Okay, go ahead. Thank you.
All right. This is Daniel Angerhausen, a friend and colleague of mine. Studied with him in Köln 20 years ago already. 15. It's 20 years ago. 20 years ago. 2007, I made my diploma thesis.
That's 15 years.
Then he went on, he was working with Sophia, the telescope mounted at an airplane. It was interesting. Afterwards, he went to the US, worked with NASA. And at the moment, he's at the ETH in Zurich, working with exoplanets as well. And he's presenting us the LIFE mission, where he's project manager.
Cool. Yeah, thanks for the introduction, Manu. So I'm going to be talking about life, the universe, and everything. So I really want to give you, hopefully after this talk, you have an idea what this LIFE mission is all about. I will give you a top-level summary, you know, also the kind of like political context, how it stands in the context of other missions. I will talk a bit about heritage. So some of the more senior people might remember concepts like TPFI or Darwin, which were very similar to life. I want to talk a bit about the roadmaps and also about the technology gaps that might be there. And I think I heard some people, for example, are working on LISA, so there might be some, you know, for example, formation flying stuff that has a similar or has a connection to this. And I will talk a bit about this this observation technique of Nulling interferometry. So I'm calling it Nulling for noobs. So really like top level introduction how this Nulling works. And then I will really start talking about the science. So I will talk first about the life detection yield. So how many Earth-like exoplanets we expect to detect with a mission like life, and then what kind of characterization science we can do with life. And if we have time, I can even show you, or I might be able to answer the question, can life detect alien civilization? So this is for you to stick with me. In the end, we might come to the little green man. Okay, so what is life? So life is one of the missions that could answer the Voyage 2050 ESA roadmap. So maybe some of you heard there was this ESA Voyage 2050 call for white papers. It's a bit similar to the decadal review in the US, where the whole community sends in white papers, and there's a senior committee looking at all the white papers, and then gives a recommendation to ESA which themes they should choose for the upcoming next 3 or 4 big class, L-class missions that they have in their portfolio. And one of the recommendations from this ESA senior committee in this Voyage 2050 report was that the atmospheres of temperate exoplanets in the mid-infrared should be top priority for ESA. It would solidify the European leadership in this field and would be an outstanding breakthrough. So one of these large mission slots, the senior committee recommended to do that kind of science, so to look for the atmosphere of terrestrial planets in the mid-infrared. And life is a mission that addresses it. So at the moment, we are planning with an array of 4 aperture telescopes, so between 2 and 3.5 meters. So they collect the light and then they combine it in this beam combiner spacecraft, where all the light is collected and then brought together and brought to interference. Typical baselines between 100 and 600 meters. So this is where the formation flying connection to LISA also comes into play. We will work in the mid-infrared, so roughly from 4 to 18, maybe to 20 micron as very low resolution. So the spectra we get are really, 20, 50, maybe to 100, and roughly split into a 2.5-year search phase. So we would be searching our local neighborhood, let's say the next 20 parsec, for terrestrial exoplanets. And then after the search phase, we would have a 2.5-year characterization phase where we pick our favorite targets out of that detection yield. And then really the goal to access habitability. So let's say, for example, derive the fraction of habitable planets that really are habitable. Of course, search for biosignatures, as the name already says. And then really just study the diversity of terrestrial exoplanets. So this is really the core to get an understanding if Venus, Mars, Earth is a typical 3 classes of terrestrial planets, or if there are even other forms that we haven't even known about. So this is roughly what life is about. And to remind you, we are looking for these pale blue dots, right? So if we observe terrestrial exoplanets, we won't get a map of them, right? We won't get a fully resolved globe of them or something. So the only thing we really get is a spectrum. So we get this one pixel, and then we can expand it in the spectrum, and then you can roughly divide it into this the optical UV optical near infrared, which is where the planet reflects the light of its host star. And then if you go to the longer wavelengths, and the second dip here starts, this is where you actually get the own emission of it. So this is light directly emitted from the planet, whereas in the visible, you mostly have reflected light. And this is roughly also how it's split between LUVA-HABEX, so this next now called, I think, the Habitable Worlds Observatory, so the thing that was chosen in the US decadal review. So they would observe this visible reflected part of the spectrum, and then LIFE would observe this directly emitted light from these planets in the mid-infrared. And this is super complementary. So this is not like in competition or anything. So we really probably need both of these missions to get a full understanding of these exoplanets. And this is something that we checked in one of the papers by the LIFE community. So this is by Björn Konrad. So we looked at what we can constrain with the different missions. So down here, you see what LUVA-HABEX can do. So this HWO, this is what LIFE could do. These are the different abundances in the atmosphere, how good we can derive them. So the black lines are always the true values. And these arrow bars show how good we can constrain them. And here are some, the planet radius, temperature, pressure, and so on. And you can see here, for example, LIFE wouldn't be able to get O2 because there's just no O2 band in the mid-infrared. But on the other hand, this optical and near-infrared emissions wouldn't be able to get CO2 and methane because they don't have absorption lines at these short wavelengths. So that's already, one thing where we are complementary. So if you, for example, looking for the combination of ozone and methane as a biosignature, you probably need both to get them. And then what's also really cool is that with LIFE, because we observe the direct emission of the planets, you can get a much better understanding of the radius. So for example, in the optical, there's a big degeneracy between a highly reflective planet or a big planet. So because it's not the black body radiation that you get here, you can never really tell, do I just have a very high albedo or do I have a big planet? So this is why the arrow bars for the radius are so big in the optical. So this is one of the great advantages of LIFE. And in the optical, you don't even get any idea of the temperature. But with LIFE, you would immediately know plus minus 10 Kelvin what the temperature of this planet is. So this is really where it's complementary and not really competing with LUVA or HABEX. And really, also we agree with the colleagues in the US that it would be the best to get both of them together. Okay, a little bit of about heritage. I mentioned that already. So some people might be reminded of some really old concepts proposed also 20 years ago. TPF, the Interferometer version, TPFI, so terrestrial planet finder, and then the Darwin mission that was proposed here in Europe to be flown between 2015 and 2025. So that would have been nice if it was accepted. One of the problems at that time was, around the 2000s, that we had no idea of the frequency of exoplanets. So that was pre-Kepler, right? So no one knew if there are even, if terrestrial planets like Earth might just be in super accident and just every 100 star would have one. So it was quite a gamble for funding agencies to build a thing like this without even knowing if there's objects to observe. And that's the first thing that changed, right? Now we have statistics of exoplanets from Kepler. We know, let's say 10% of FGK stars have planets in the habitable zone that have roughly the size of Earth. That's the first thing that changed. And of course, there was progress made in a lot of these key technologies. And this is why people like us revisited these old concepts and look, with the new statistics, with the new technology, how feasible are these old ideas today? And this is where we are coming from with LIFE. So roughly the idea would be, so you are here somewhere. So we just said, James Webb started, we get Roman soon, and Plato and Ariel, which some of you already mentioned, are also working on. And then in the future, we would get this Habitable Worlds Observer, and then something like LIFE in this NASA roadmap, still called the Exo-Earth Interferometer, and then again, getting the reflected light first, and then hopefully soon after the thermal emission. You can see this is really, here we would get the first idea of some biosignatures, and here with this mid-infrared we would really get to this live verification if it's out there. Just to briefly mention the technology, I know this is not a big crowd of engineers here, so really just a couple of these technologies that we are working on. So if anyone is here, I'm happy to nerd out about all these parts if you're in the lab and do some cryo experiments, but I'm not sure if that's the main crowd here. So one big technology gap to fill is formation flying. So it would be cool if some of the LISA folks maybe share their expertise with it. We need super sensitive detectors. So an Earth around the sun at 10 parsec gives you roughly 1 photon per minute per square meter per micron. So that means you can really give each photon a name, right? So every 60 seconds, there's like 1 photon coming. So you need a really, really good detector to really get these technically single photons that you're counting. Since we're in the mid-infrared, a lot of this stuff needs to be cooled. So a lot of our elements need to be cooled. So there's also, a lot of expertise from James Webb now, because it's also in the mid-infrared and a lot of the stuff needs to be cooled. And then we also need high sensitivity in the beam combination. So how we combine the 4 beams, the 4 apertures that build the telescope. So these are some of the technology pieces that we are also working on. We just won a big grant, or 3 million, quite big grant in Switzerland, to work on the cryo experiment mostly. So we have an experiment called NICE, the Nulling Interferometer Cryogenic Experiment. So we are pretty good at our acronym game. So this is what we are doing at ETH right now to really prove this nulling concept in the lab, that it works at these low temperatures. Okay, so since I mentioned that, so how does interferometry work, or nulling interferometry work? So really just top level. First order, so if you have 2 telescopes, you have essentially something similar to this double slit experiment that you might remember from this, right? So you get these streaks of interference. So you get parts where the signals get add up and parts where the signal cancel out. So now what happens in nulling interferometry is you put a phase inversion in there. So between the 2 telescopes, you would put a phase inversion, and then you get these areas of destructive interference for everything that's on axis. So if you focus or if you point at the star would be canceled out, and then the planet would be falling in this area of transmission. So this is essentially how it works. So you have this normal interferometer. So this would be imaging interferometer where you just add the signal, but by adding this phase inversion, you get to a nulling interferometer where the light of the star gets canceled out. However, you wouldn't see that planet yet. I mean, it has transmission, but you wouldn't really see the signal. So what we then do in practice is actually rotate our field of view and then observe the planet, how it walks between dark parts or low transmission, high transmission, low transmission, high transmission, and then you get like almost like a time series observation. This is what's shown here. So you essentially rotate your field of view, and then your planet moves around through these areas of transmission and no transmission, while your star is still suppressed, and then you get this time series or transmission observation depending on your rotation. And this is in the end how a planet detected with a nulling interferometer would look like. And this is for 2 telescopes. So if you take 3 or 5 or 6 telescopes, it gets arbitrarily more complicated. So the message here is it gets complicated. So you get like not just transmission map like this, but you can get all sorts of crazy transmission maps that might have some advantages depending on how easy it is to rotate them, or how easy it is to distract or to extract the planetary signal. But the main idea is really coming back to this, is that you have this phase shift and suppress the stellar light. So this is all you should remember, or if you don't even remember that, just remember it gets you mid-infrared spectra of exoplanet, and we get to the engineers. Okay, so this is where we come to the science. So if there's any questions about it, I'm happy to explain a bit more, but I thought we just do a quick excursion how this works. So now I will focus mostly on the science for the rest of the talk. So what it takes and what life does in detecting and characterizing terrestrial temperate planets. And this is in essence just summarizing this LIFE paper series. So in this LIFE initiative, in this LIFE consortium. We are now at, I think, paper 10 or paper 11 is close to submission. So we have 10 papers accepted and a bunch more in the pipeline. So it's really, after a couple of years, we are really producing a lot of science and a lot of output in terms of paper, and it's really diverse. So it's really from general introduction to some of these papers that look at the technology. Some papers look at individual experiments, and I'm going to introduce a couple of these papers that we have in this series. So the first, of course, and that's usually a bit of a sanity test. For a mission like this, you would start asking how many planets would life even find. So if I build life, look at our neighborhood, let's say everything within 20 parsec, 30 parsec, how many planets would I detect, right? This is the first sanity check you do. If you can't find anything, you don't build the mission. And this is what the first life paper calculated. So this, based on Monte Carlo simulations, based on the Kepler statistics. So Kepler gives us a decent idea, what the frequency of planets around stars is, and then you use this, simulate 1,000 universes, so 1,000 local universes, add planets everywhere, and then check if you can observe them, find them or not. And then you do that a couple of times, and then you can average over it, and then you get some number of planets that you detect. So in comparison to the LUVA and HABEX studies here, you can see life is pretty much in the same ballpark. So we will find, depending on the scenario, so this scenario we would maximize on number of planets that we, the number of planets that we would find in this scenario, we would focus on finding habitable zone planets. So we would find much less here, but much more habitable zone planets. So we can kind of tweak our observing strategy to find more of depending on what we find more. But the take-home message here is we will find hundreds of new planets, and 70 of them sub-Jovians, 200 sub-Neptunes, and then really 200, let's say, in this rocky and super Earth regime that is potentially the most interesting, depending on what you come from. So this is the first lesson that we learned, pretty optimistic, or a pretty good answer for us, so that if you use life in this baseline scenario of 2-meter telescopes only, you would already find hundreds of new planets. And then some of them, at least dozens, will be temperate rocky planets. So I'm not saying habitable zone planets because this is a whole other can of worm, but I say temperate rocky planets. So the right size, the right temperature to have liquid water on the oceans. Most of them only accessible with life. So if you compare to LUVA, HABEX, or this NWO, a lot of these planets would only be detected with life. So for some reasons, we are much more sensitive, especially to these early types, so late type M-star planets, which HWO wouldn't get. And I showed you this plot. So this is a typical sample of habitable zone planets. So depending on the definition, so if it's the optimal habitable zone, the conservative, or the optimistic habitable zone, the conservative habitable zone, or exo-Earth candidates, which is an even narrower definition, you get between 10 and 20 of these around M stars within 3 to 6 parsec. So we might even get one that is really close, so within 3 parsec. That would be probably one of our golden targets, and I'll talk a bit more about this in a couple of slides. And then for FGK stars, the closest one would probably be in 3 to 6 parsecs, so still relatively close by. And then we get, about a dozen farther out between 6 and 10 parsec, let's say. So this is going to be the sample of potentially habitable planets that we would be working with this life. So in the order of a couple of dozens, 30 to 50 maybe, habitable planets that we would be able to follow up, then not just find them, but then in the next step also characterize. And just as the message that I already mentioned, so life is really, really good for cool stars. So if you're interested in M stars, if M stars is your science case, or planets around M stars is your science case, then you also got to love life, because life is really going to be the only telescope that can get so close in, because we don't have for the more technically speaking people, so we have a much smaller inner working angle. So that's why we are much better, or have a huge advantage over these coronagraphic missions. And this is why we can really good have a really good use of life for M-star planets. So if you love M-stars, you've got to love life. Okay, then let's come to the characterization phase. So this is really once we have found these planets, once we have these 30 habitable zone planets, what kind of science can you do, right? So what kind of characterization, besides just knowing that they are and getting some statistics, and what can life find on these planets? And the first sanity check again for these kind of things is, would we even be able to observe Earth, right? This is similar to, do we find anything? And if we find it, what can we learn? Can we distinguish Earth from Mars? Can we distinguish Earth over its geologic time scale? And that was one of the first two experiments that we did. So the paper by Björn Konrad and by Eleonora Allais, where we looked at first just Earth. So if you put an Earth around a G star at 10 parsec, would we find methane? Would we find oxygen? Would we find CO2 in the atmosphere? And the short answer is yes. And then in Eleonora's paper, we even looked a bit further and looked at Earth at different geologic times, right? So prebiotic Earth here, then Earth right after the oxygenation event or during the oxygenation event, and then another one right before the second oxygenation. And we can clearly distinguish all these four phases, which is also interesting. So we can even not just say it's an Earth-like planet, we can say it's a prebiotic Earth, or it's a Earth right after oxygenation or something like this. And in all of these cases, or at least like the ones, not the prebiotic ones, but even in these two, we can also find this combination of methane and oxygen. So we can clearly see that there's something weird going on, which may or may not be, a detection of life in that context. But that was already pretty comforting for us. Then Björn just got accepted. I think it's coming out soon, the paper where we looked at Venus. So we again looked at if we have an exovenus at 10 parsec around a G star, what could we observe? How problematic would it be that it's so cloudy? Can we break the degeneracies? Can we even look to the surface? So this is also super interesting. So the take-home message from that paper is that the clouds sometimes are hard to distinguish from the surface. I mean, that's kind of like what you would think, right? You look on something and then you can say if it's a cloud top or if it's really the surface of the planet. So that makes it hard to really get the size of the planet. But when it comes to the abundances, so if it comes to detecting water or CO2 in the atmosphere, we can still get the abundances pretty good, even if you just observe on top of the clouds. So that's roughly the take-home messages from that paper. Then we just had a paper accepted by Michael Jansson about imaging of exocomets. So this is also pretty busy plot here. So these are all these comets, I think in beta pig or something, he simulated it. And then these are these interferograms that I mentioned, right? So if you rotate this in our transmission map, you will get all these crazy signals here. And then according to this paper, we should be able to even observe these comets in this system. So that's something life could do. And then we looked at a bunch of biosignature gases, if we can observe them and how long it would take. So one paper that I published just recently, so we looked at phosphine, which was quite famous 2-3 years ago when it was supposedly found in Venus. And it's one of these biosignature gases that might be an interesting thing to find in an exoplanet, because under certain circumstances, especially on super Earths and smaller planets, it's the only reason to explain a large quantity of phosphine would be some biogenic fluxes, so some microbes producing it. In giant planets, there are some mechanisms where it gets up from the inner parts of some convection gets phosphine up. So interesting in that context would also to figure out where this transition region is, where you don't have any abiotic phosphine anymore. So we looked at what would it take to do a phosphine survey, right? So we checked, if you look at a Jupiter-sized G star, a planet around a G star at 10 parsec, that is 500K in that case, it only takes 1 hour. So I do 1 hour observation of this warm Jupiter, and I would find phosphine. If you go to the super Earth around M stars at 5 parsec, the CO2 or hydrogen-dominated atmospheres in the super Earth, it would take only about 10 hours to find or to distinguish a case with phosphine to a case without phosphine. But if it comes to a Venus twin at 10 parsec, and even if you put like a lot of phosphine in the atmosphere, it would be super, super hard to observe this. So this was roughly our estimate here. And these were pretty straightforward observations. So as I mentioned, we just looked at a spectrum with phosphine and the spectrum without phosphine, simulated the noise, and then got the difference between with and without phosphine in units of our sigma. And then once it gets over 3 sigma, we can say, okay, there's a detection. So just to explain, on the top, it shows what configuration we are looking at. This shows how long we're looking at. So here it was really just 10 hours to get this spectrum of the planet. And then here you see the difference between phosphine and no phosphine in units of sigma. So here's the 3 sigma lines. You can see here, these lines go over the 3 sigma threshold. And if you band integrate it, it should be a pretty solid detection of phosphine in this case. And right now we are doing a similar exercise for a couple of other molecules. So this is nitrous oxide. Again, something that if you detect it in high quantities, can really only be produced by a biosphere. So we simulated full climate models with different fluxes of N2O. So 1 teramole per year is roughly 50% of the Earth's biosphere, and then 100 teramole per year would be twice what the Earth's biosphere would produce if everything was gone into nitrous oxide. So roughly supposedly realistic scenarios. And here we looked at the Earth around a G star at 5 parsec, and here we observed 100 days. So in 100 days, we would clearly get these detections of this N2O. But what is a bit harder is to also get the ozone. You see here, this is the ozone feature. These are the N2O features. So you can get this very big fingerprint here, and these smaller ones of nitrous oxide. But to really also detect this methane bump, this ozone bump here, to get the combination of nitrous oxide and ozone takes maybe even a bit longer than the 100 days. But at least in principle, it's feasible. And this is also a G star at 5 parsec. It gets a bit easier for M stars. We also looked at methylated halogens, so CH3X, so like methane, but you replace one of the hydrogen atoms with something else. So in this case, we looked at methylated chloride, so CH3Cl, and CH3 bromide, so methylated bromide. And here you can see the spectra. It's a bit busy, this confetti plot here, but we can also find all of these different scenarios with different, you can distinguish them pretty well with different fractions of these methylated halogens. And this is actually calculated for Earth around Proxima Centauri. You can see here, and this is the coolest what I think is very cool came out of this study. So here it takes only 1 day. So if we had an Earth around Proxima Centauri, or let's say for one of these super golden targets, if we find a habitable planet, let's say at 2-3 parsec, then we can really do these kinds of observation in really, really short time scales. So this means we should even be able to look at some sort of weather or seasons in these planets. So if anyone is working on, let's say, how flares interact with planetary atmospheres, that would be something super interesting for me to see if we can observe that with light. So probably for these M-star planets, they are circularized. There's not going to be seasons as we know them from the Earth. But I think what might be the driver for seasonality on these M-star planets are flares, or is the stellar activity. And what I think could be possible with this, spectral temporal resolution of 24 hours could really be to look at an atmosphere reacting to a flare. Right? You have a flare that, let's say, destroys all the nitrous oxide in the upper atmosphere, and then the biogenic flux eventually replenishes it over weeks, and you can observe how that happens, for example. That would be super interesting if anyone works on star-planet interaction. That would be something what I think would be really nice to simulate with our live observations here. What I'm currently working on, and this is all work in progress, is to look at the significance of a null result. So let's say we observe these 20-30 planets in our neighborhood, and we don't find life on any of them, or we don't even find water on any of them. Then we could at least, then the question is, how many planets are enough to make at least the null result somehow significant? And this is the eta observable, so the fraction of either habitable planets or fraction of planets with life, depending on how many null observations you had. So if, let's say, we observe 30 planets, we don't find life or we don't find water on any of them, this is how good we could constrain the fraction of habitable planets or the fraction of planets with life by using different priors. So if you use a uniform base Laplace flat prior or different Jeffrey priors, it makes a slight difference here, depending on how optimistic or pessimistic you are. But it shows that, let's say, if we have 30 planets and we don't find life or oceans on any of them, we can at least constrain, let's say, the frequency of habitable planets by, to 20% or slower. So this is the best fit here. This is big line, and this is the different upper limits, 99.9% upper limits, depending on what prior you choose. And then you can zoom in a bit, and then you can see here, yeah, depending on how nitpicky you are, you can say, yeah, I think after 30 planets, we get kind of independent of our priors, and we probably need at least 20 to make, some decent answer here. So this is also something we are looking in right now. Yeah, and then I promised you the aliens, right? So you all want to hear about the aliens. So what that means is we actually also looked at detecting so-called technosignatures with life. And this is essentially the same as these biosignature gases I talked about before, but instead of large pool of microbes, these are molecules that can only be produced by technology. So let's assume there's like a civilization that's even crazier than our civilization, and they live at the outer edge of their habitable zone, and they want to heat up their planet because it's getting too cold over time. They put some extra gases in the atmosphere to geoengineer it. Would be detected? And the answer is yes. So we looked at one, that's a pretty crazy planet. So it's an Earth planet around an M star at 5 parsec, which has 100 times the CFCs in the atmosphere. So the stuff that we have in the fridges and in hairspray that causes the ozone hole. So if there was a crazy civilization that puts 100 times of it in the atmosphere, we would in principle be able with life to distinguish or to measure CFCs in the atmosphere, and similar for SF6 and C3F6, so very complex molecules that you can only produce in industrial processes that are also greenhouse gases. So again, the scenario here is it's a geoengineering civilization that puts a lot of that stuff in the atmosphere to make it warmer or colder or whatever. And we also would be able to detect this. So this is, it's a fun experiment, right? It's a bit of a thought experiment, but in principle, life is sensitive enough to find these crazy civilizations if they were there, and with pretty high significance here even. Okay, so that's pretty much it. So a couple of take-home messages, so reasons why you should love life. So what you can do for life. So if you run planet models, climate models, if you have similar models with and without a feature, we can easily produce similar plots. So if you, have snowball compared to an ocean planet, something like this, I'm happy to, help you simulating them. And then, as I mentioned, these temporal dynamic changes, so this reaction to flares, that is something I'm super interested in. So if anyone is modeling planet-star interaction, I would be really interested in that. And then also something we are looking at is from individual planets to demographics. So we have one project where we look at if life could even prove something like the habitable zone concept. So the assumption that the farther out you get from the planet, the more CO2 you get to get the planet warmer. So if we have predicted trends like that, so higher insolation, a lower insolation, more CO2, or in other cases, maybe for intermediate sized planet, there might be more metal equals more clouds. So whatever demographics or large scale predictions we have, we also want to check how many planets, similar to what I showed before, do we need? How good do we need to find in the individual features to prove these trends? And then within the life community, so we are super open. Lots of early career scientists actually in the group. So there are many jobs. So in the project office, there's a bunch of stuff to do. We're still looking for a working group and sub-working group leads that pick some of these topics and work on them. And really, it's from mid-infrared detectors to emission spectra of microbes. So whatever your background is, there might be some way to contribute to this huge effort that life is. So in the next decades, we will have the technologies to systematically search for potential biosignatures. And LIFE is a European-led initiative. One of the most promising concepts in this field. If you ask me, I'm obviously biased. We're already quite a big group, so we are about 200 people, obviously with different levels of commitment, but we are all over the world. Even in Australia and Japan, we have collaborators that work with us. A bunch of us, of course, in Europe. Yeah, so if you're interested, check out our webpage, sign up for our newsletter, follow LIFE on Twitter, and that's pretty much it. So I just also a backup slide. Yeah, so I'll let the summary slide up here, and thank you for your attention. Questions about LIFE? Questions about LIFE? Only in all caps. To other LIFE questions, you're on your own.
Yeah, this characterization of case is right. The funny structure only.
Yeah. Yeah. Well, that's a great question. So there's actually a paper on this. So Oscar, what's his name? Carrion Gonzalez, I think he's working on this right now. So he looks, first of all, which of the known planets we can already observe with LIFE, and then also which planets we can observe with HWO and LIFE, or just with HWO and LIFE on its own. And there's already a bunch of planets. We could start now without any detection. So in principle, and we are still hoping that by the time that LIFE flies, there are so many planets. Carmen is probably hopefully going to give us more, especially these Earth-like planets around M stars. Then the more planets other surveys find, the less detection phase we need to do. So in the best case, we would completely skip the detection phase and just characterize known planets. But if you submit a mission like this, you have to be self-sustainable, right? So we have to assume worst case scenario, there's no other planets known, so we find them ourselves. But if other surveys find them before LIFE launches, great, right? Then we just skip the detection phase and have 2 years more to characterize that. Yeah, and this paper by Oscar should be coming out soon. So that really does this. He has like big tables, which like all known planets from the Exoplanet archive, if they're observable with LIFE or not. So yeah.
Is there any difference in the tables when you know the ones? With LIFE, you do not have any knowledge.
Of what? Of the mass?
The mass and the radius.
So radius we get pretty good. So this is, I think, the thing I showed in the beginning. Let me go back to this slide. So let's.
Okay, so from the
Yeah. So I mean, it's because we observe in the mid. Oh, no, it's done. Yeah. So here, right? So with LIFE, we are pretty good at the radius. So we nail the radius, within plus minus, 5% or something like this, and also the temperature, because we observe in the mid-infrared, we, get to feel a black body if you want to simplify, right? So this is really, really good. Whereas in the optical, that's a big problem because you have this degeneracy between, clouds and albedo and radius essentially. So that's pretty good, yeah. And then, of course, if you have this huge error bars, it makes the retrievals much harder. Or sometimes you even have degeneracies or two modes, right? So then you run a retrieval and you get in your posteriors two minima, like even a big planet that has lots of CO2 or a small planet that has a lot of methane or whatever, right? So you get these ambiguities, and the more you can constrain these basic parameters, the easier it makes the retrieval. I also bought another project, so I'm also doing a lot of machine learning stuff. So if you want to look at the poster, I'm exercising my poster. I'm going to the Beacon conference on La Palma next week, so I have to training in front of my poster. So if anyone wants to simulate a poster session with me, you can come to the front after.
Okay. Thank you.
Didn't check if there were questions.
All right.
Well, I guess I look out then.
Ja, das ist schon gemacht.